This is Dr. Alsaffar. This is ITCS 255 Discrete Structure 2. Today's lesson is about recurrence relations. I will start by giving you two examples. One is how to describe and what is a recurrence relation when we describe it mathematically. The second example, how recurrence relations are related to algorithms. So as an example, suppose we have the following sequence. It is -1, 1, 3, 5, 7, 9, 11, and we continue. Our job is to describe this sequence mathematically. We will label or we will put index for these numbers. So here we are going to have an index for the location of each number. So the index for -1, it doesn't matter, you start from 0, from 1, from 2, doesn't matter. But usually for recurrence relations, commonly either you start with 0 or you start with 1. So I will start with 0. And the next one is 1, next one is 2, next one is 3, 4, 5, 6, and it continues. For the sequence, you have to give it a name. You have to give it a label. So mathematically, you have to give it a label. So I'm going to call this sequence A. So any number in the sequence can be described as an index like an arrays. Okay, in arrays, how to locate an element inside the array, you use the index. So A, maybe you can imagine it as a name of an array, and N is the index. So how to relate, this is how we want to describe it mathematically. You have to understand how these numbers are related to their previous values. How 11 is related to previous values. Maybe previous value by 1, or maybe you should go by 2, or you should go by 3. This is a very simple sequence, so it is very easy to describe it and it's very easy to find a pattern. Now if I ask you what will be next after 11, or directly you will tell me it is 13. How did you find it? Because every number, when you add 2 to it, it will give you the next number. So if I want to describe it, then suppose for example 7. How we find 7? We can take the previous value and add 2 into it. So jumping from here to here, you add 2. So if you want to describe it, if an is the current value in the sequence, so how to go back one element, you write an -1. And how to find the current value from previous value, you go to the previous value by 1 and then you add 2. And this can happen for every number. So if you want to find, for example, let's say here I want to find A6. Then A6 is equal to A5 plus 2. So find the value A5, add 2 into it, and you will get 6. But this cannot be applied on the first number in the sequence. So for example, this one, we cannot apply this equation because if I put A0, then there is no A -1. So this is like a special case. This is called initial value. I need a space here. Initial value. Okay. So I need to describe the first one outside this equation. We cannot just include it because we cannot apply the first number on it. So I will start saying that first A0 is given separately, which is equal to -1. In this case, this equation, what is the first value for n? Because A0 is the first value, so the next one is 1. So that means this equation will be applied for all n greater than or equal to 1. This equation, I will just put a cloud around it, is called recurrence relation. This is our definition for a recurrence relation. A recurrence relation is a sequence such that every element in the sequence is described by its predecessors. This is a very simple one, so it's easy to find the sequence. Sometimes there are very difficult sequences that you cannot see the pattern. If you want to find any number in the sequence, for example, if I ask you find A5, from the equation A5 is equal to A4 plus 2, so you need to know A4. And if you want to find A4, then you need to know A3. And if you want to know A3, so in other words, if you want to know any number in the sequence, you have to know all numbers in the sequence before that number, predecessors. Is there an equation that it does not depend on the previous values? It depends only on the current position. So imagine the following, and it is called a closed form equation. So here we have closed form equation for AN, and AN is the recurrence relation. So what is this closed form equation? It should describe all numbers in the sequence, not only the initial value, all numbers in the sequence. By looking at the numbers, they are odd numbers. So -1, 1, 3, odd numbers. So the first thing you think about that all numbers are odd, and you can describe odd either by 2k minus 1 or 2k plus 1. So we will say that AN is equal to 2 multiplied by n minus 1, and for this equation I should know what is the first value for n. Remember that, or just if you go back to the sequence, the first value you have it at index 0, it gives you -1. So how can I get -1 from here? What is the value of n? So when you plug it here, you get -1, and it is very simple to find it. It is 0. So this equation is applicable to all numbers in the sequence, and we call this equation a closed form equation for AN. So it looks like a solution. So this is a solution. So this is a solution to the recurrence relation AN, and it is easy to find any numbers in the sequence if you want to find its value. For example, if I want to find 100, so simply multiply 2 by 100, which is 200 minus 1, it will be 199. Imagine you want to find 100 from this sequence. Then you have to know A99, A98, all the way down until you go to the initial value. Our next question before we start the second example: if you are given a recurrence relation and its solution, how to prove that it is really a solution to the recurrence relation? So here we will write a question here, okay, as an example. So this is our next example. Prove that the recurrence relation that we have just solved, A0 equal to -1, AN is equal to AN minus 1 plus 2, n greater than 1, has the solution AN equal to 2n minus 1, and n starts from 0. So the recurrence relation can be described in two forms, as a recurrence relation, as a sequence, and as a closed form equation. You can prove it by using two methods. One is by simple substitution, and the second one is by induction. And you have learned in discrete structures 1, when they give you a question on induction, they give you on sequence, and you used it in that course. So there is a simple way to prove that AN is the solution to this recurrence relation by substituting. So we will start with the recurrence relation since AN is equal to AN minus 1 plus 2. On one side, this is one side. What is the value of AN minus 1 from here? From this equation. If this is n and it has AN is equal to 2n minus 1, then what if I remove n and replace it by n minus 1? Then you have to remove this n also and replace it by what? N minus 1. And this is what we will do. We will substitute this in here. So this is equal to 2 multiplied by n minus 1 plus 2. And I will put a label here below this equation to tell you that this is the equation for AN minus 1, and we found it from AN. We found it from here. Now simplify the equation. So this is equal, I need to move it a little bit up. Okay, it's taking space. So this is equal to 2n minus 2 minus 1 plus 2. This 2 with minus 2 will go together, and we will have this is equal to 2n minus 1, and this is equal to AN again. So when you substitute for AN minus 1 for the solution, you will end up also with the same equations on both sides. So this is a proof that this is a solution to the recurrence relation. Our next example is to show you how recurrence relations are related to algorithms. So again, as an example, so here example, write a Java code to find the summation of, this is the summation, I'm going to call it S, okay, S, there is no need now to call it S, just to find the summation that starts from 1 up to n of I. So this is our question. So we will write the code in Java. So it will be a loop, integer, where we put a variable sum equal to 0, and we write a for loop, a very simple for loop that starts from 1 up to or equal to n, I plus a plus, and then inside we write sum equal sum plus 1. So it's a very simple program, very simple code that it finds the summation from 1 to n. If we ask you to find the running time of this algorithm using growth functions, then this is a linear because the loop goes from 1 to n, so it will be big O of n. Now how to describe this summation in as a recurrence relation? If we look at the variable sum, okay, notice it is a start number is 0. So let me call this sequence S. So we will write S, this is the beginning, okay. So as a recurrence relation, we will write, I will just write a title for that, okay, recurrence relation, we would like to describe this code as follows. I will label the variable s, or the recurrence relation s. So the first value of s is 0. So we will have s0 is equal to 0. And this is coming from here. Now for any subsequent number, so here this subsequent number, so here I will put a label so that you can remember. This is the old value, or we say the previous value, and probably it's better if I call it the previous value, predecessor, previous value, and this is the new value. So to get the new value, we get it from the previous value plus 1. How we describe this by a recurrence relation? We say if we want to know the sum at n, so the loop goes up to n, maybe I can call it I. Then it is the previous value plus 1. And this will start for n from 1, and this is why we write the loop that starts from 1. So this is the recurrence relation that we found from this code. If I want to write the summation as a recursive function, so here we will write this code as a recursive function. Okay? Recursive function or method. Okay, recursive function. In Java, it is called method. Then it is very simple to implement it. We will define the name of the method and we will call it sum, and it has the input parameter n. Now you know that for recursion, eventually the recursive call will terminate at a termination condition, and this termination condition is here. So we write if n equal 0, then return 0. Otherwise, we will call the method sum n minus 1 plus 1, and we will call it recursively. So it is a copy, just exactly the definition you have found for the description you have found for the recurrence relation. You can implement it directly. So what is the relationship between, why we are interested, okay, to convert into sequence? Because there are some recursive functions. If this recursive function is described using this recurrence relation, we are so interested to know the timing, the running time of this algorithm. So you need to convert it into its solution, and you know that its solution will be expressed in terms of n, and then from the solution we can say what is the growth function or what is the big O of this algorithm. So basically this is why we are interested for recurrence relations, that if we have a recurrence relation, we need to find its solution. For your information, there is a website. I would like you to have a look into it. And the website is not only useful for math, it is useful for any science. You just give it the recurrence relation and it will give you the solution. So what is the site? It is www.wolframalpha.com. Let me show you this website. This is the website, Wolfram Alpha. You see on top is the address, www.wolframalpha. And as you see on the front, it is not only for mathematics, but I am now on mathematics. You can use it for physics, you can use it for arts and media, and etc. So inside this text box, I'm going to write the recurrence relation that we have discussed in our example, and this is how we describe it. The name will be A, and between round the brackets 0 the initial value, and it was -1. you put comma, and now you describe your recurrence relation. As you notice, it is giving you an example here. So a n is equal to the previous value of a, which is n minus 1, plus 2. And now when you press enter, then it will be connected to the server. It will do the calculation and will give you result on the screen. So see, now it is showing you. Unfortunately, the pointer is not working on the website. But see here, it says A0 equal minus 1 up to here. And see the solution, it says recurrence equation solution is an equal to 2n minus 1. And also it shows you some of the numbers, the initial numbers, C minus 1, 1, 3, 5, and 7, and etc. So this is for free, but there are some functionalities. If you would like to activate them, then you have to pay money for it. For example, enlarge, and or if you want to see the steps, okay, for your solution, then you have to pay money for it. You can download an app on Android and iOS. On iOS, I think it is $3. So you can use it on your mobile or on your iPad. So a recurrence relation for a sequence A0, A1, AN is just an equation that relates AN to its predecessors. When we say predecessors, it means the previous value. So if AN is here, then all values before AN will be predecessors. So starting from A0, A1 up to AN minus 1. Here are some examples on some functions that we can describe them recursively. Let me go over them quickly. So our first example will be the power of 2. So examples, the first one, we have AN, and I'm going to call it AN, is equal to 2n, okay? And if I go back to the slide, so we have AN, it starts from, and we can find it from where does it start. Because if you see here, it depends on what you want your sequence. Suppose your sequence you wanted 1. So suppose that AN, you wanted 1, 2, 4, 8, 16, and etc. So this is what you want for your sequence. And by the way, you can start from 2. If n is equal to 1, if n greater than or equal to 1, then you will start from 2, etc. But if you start from 0, you are going to get this. So how to describe it recursively? On one side, ask yourself, if this is AN, then what is AN? What is the equation for AN minus 1? The answer is AN minus 1 is equal to the power n minus 1, and you can find it easily from here. You remove n and put n minus 1. So we will start from AN equal to 2n, and this is equal to 2 multiplied by 2 n minus 1, and since n minus 1 is equal to an minus 1, so we will have 2 multiplied by an minus 1. Then we can say that an is equal to twice the previous value. But what will be the initial value? And are we going to give it 0 or 1 and etc.? So we are going to give it as 0, because anything raised to power 0 is 1. And in here we will start from 1. So this is how it is described recursively. If you go to the next example, it is for factorial. Now for factorial, the second example, so number 2, we have number 2. If we label the factorial as an, so what will be an minus 1? It will be n minus 1 factorial. So we will start by defining an, since an is equal to n factorial, and we all know that n factorial is equal to n multiplied by n minus 1 factorial. But n minus 1 factorial is the value of an minus 1. So you can simply remove n minus 1 and replace it by n minus 1. So this is the value of an. The question is, what will be the initial value? So we will start from 1. We assume the first, because when you multiply, or if you want to find factorial for any value, the last value is 1. So we will write it in reverse order, 1 times 2 times 3 up to n. So here we will start from 2. And this is the recurrence relation. Maybe I can cloud it. So this is the recurrence relation for the factorial. And this is the recurrence relation for the power n. The third example is a very famous sequence, which is called Fibonacci sequence. So I will copy it, take it to our notebook. Okay, so how to describe it by numbers? We will start from 0, so index 0 and index 1. So we will have f1 and we will have f2, f0, f1, f2, f3, f4, and we continue. The first two values are equal to 1. And it says that for any number in the sequence, you take the previous values, immediately previous values, and you add them together. So the previous value for f2 will be 1 plus 1, so the answer will be 2. The previous values for f3 will be f1 and f2. When you add them, you get 3. The previous values for f4 will be f2 and f3. When you add them, you get 5. You will get 8, and you will get 13. You will get 21, and it continues. What we will do next is we are going to show you how to find a solution for recurrence relations. There are many methods. Some of them depends on understanding some math basics. So I will go over some of the math basics, and then we will discuss the methods for finding a solution to a recurrence relation. The first two equations that we need to understand is the geometric series and the arithmetic series. So what are these series? The first series is the arithmetic series, and why we need a closed form formula for the series. So this is our series. Now if you want to find, let's say, summation from 0 up to 100, then you need to expand the summation by writing when I is 0, then 0 plus 1 plus 2 up to 100. So that means you have to know all the numbers from 0 up to 100, add them together, you get an answer. Is there an easy way to find the answer without going to the previous values? Yes, which is this equation. So this equation says that you can find the answer. N is 100. So simply substitute. It would be 100 multiplied by 101. You divide it over 2 and you will get the answer directly. So how we can find this equation from the sequence? This is for your information. I'm just providing that thing for you to understand how we got this equation. Let us label S as 1. And by the way, you can start from 0 and you can start from 1. It will not change the addition, because 0 added with any number, it will not change the result. So I will assume that we have 1 plus 2 plus 3 up to n. And remember, we will go up to n minus 1, and then we will go up to n. Now write the same S, but in reverse order. So start from n, then go to the next one, which is n minus 1, go to the next one, which is n minus 2, and keep doing this until you reach 2 plus 1. Now add them together. So when you add them together, you are going to get 2s. And probably I should write it explicitly. add s plus s, and it's going to be equal to 2s. So when you add them, we will combine these two together. We will combine these two together. We will combine these two together. And at the end, we will combine these two together, and we will combine these two together. So we will take them into pairs. So the first pair will be n plus 1. And this is coming from here. Now the second pair will be also n plus 1. The third pair is also n plus 1. And if you keep continuing this, then you will have n plus 1 as the last one. So how many n plus 1 do we have? Here in total we have, this is n times. So s plus s is equal to 2s, and here on the other side we will have n multiplied by n plus 1. So what is s is equal to? It is n times n plus 1 divided by 2, and this is the one that we want to find. For the other sequence, this is our sequence. First, we need to expand it so that we can understand it, how it looks like. So s is equal to, when I is 0, see, when I is 0, then r raised to power 0 is 1. Now when I is 1, r raised to power 1 is 1, is r, sorry. And then the next one will be r squared, the next one will be r to the power 3. And as you notice, it goes up to n minus 1. So the last one will be n r n minus 2 r n minus 1. This is the last one. Now multiply s by r. So multiply s by r. So we will have shifting to the number. So 1 multiplied by r is r. R multiplied by r is r squared. R squared multiplied by r is r cubed. And it continues. And remember that for the last one will be rn, because rn minus 1 multiplied by n by r, it will be rn. Now subtract s minus rs. So combine these two, subtract these two, this is equal to 0. Subtract these two, it will be equal to 0. Subtract these two, it's equal to 0. And again, you will subtract these two, it will be equal to 0. So this one is already subtracted from the previous value in here. So what is the equation that we are going to get? First, we will put 1 as an answer. Then we have 0 for this part, and we have 0 all the way until the last one is 0. And for the last one, if you notice here, there is no corresponding value for Rn on top. So the answer will be equal to minus Rn. So S minus Rs is equal to 1 minus R raised to power n. Now you arrange, multiply both sides by a negative number. So we will have Rs minus S equal to Rn minus 1. So therefore S is equal to Rn, and maybe I should put one take S as common, so it will be R minus 1 is equal to Rn minus 1. So S is equal to Rn minus 1 over R minus 1. And remember, R should not be equal to 1. And this is the equation that we are going to use for the geometric sequence. A question is raised here. What if r is equal to 1? If r is equal to 1, then you have to go back to the original definition here and put 1. So when r is 1, so anything raised to power, so 1 raised to power anything is 1. So it means that you are adding 1 n times, so the answer is 1. So if r, I will write here, if r is equal to 1, then s is equal to n. Otherwise, if r is not equal to 1, then this is the equation we have for the geometric sequence. Now, what if the indices of these summations are not the same? Okay, for example, suppose we ask the following question. So here is an example. Find the summation for I equal 1 up to n minus 1 for I, and summation that I starts from 3 and it goes up to n, let's say also minus 1 for I. So as you notice that this one starts from 1, but this one does not start from 1. So what was the summation? We had the arithmetic summation I equal 1 up to n, and this was the equation. So how to find a closed form equation for these two? If you have a summation like the first example, if it starts from 1, then it is easy to find the closed form summation. And notice this goes up to n and this goes up to n minus 1. So what you have to do? So I will just copy it, and then we will start from here. Paste. So this is going to be equal now. I will put on one side and then I will erase it. Summation for I equal up to ni is equal to n times n plus 1 over 2. So both starts with 1. So all what you have to do now for this equation, remove n and put n minus 1 anywhere, both sides. So instead of n, put n minus 1. Instead of n, put n minus 1. So the result that you will get when you replace n by n minus 1, it will be n minus 1. And here when you put n minus 1 plus 1, it will be equal to n. So multiply it by n and divide it by 2. So it is a very simple substitution as long as the start value are the same. Now for the second one, which it does not start from 1, it starts from 3. Okay, and if it does not start from 1, it starts from 3, then we need to do an adjustment. Okay, so we need to do an adjustment so that we can make it start from 1 instead of starting from 3. Now the number of terms that we are going to have here should both be the same. So this one starts from 3, it terminates at n minus 1. The number of terms that we are going to add should be exactly the same if we start from 1 up to, and we have to see what is the value here. Let's go for the initial value first. Here this one, the first value, when I is equal to 3, the first value is a 3. So how can I get a 3 when I is equal to 1? It is very simple calculation. It will be I plus 2. So when you substitute 1 in here, you will get a 3, and this is the first value you will get here. Now for the last value, how to find it? Remember that the last value in this summation is n minus 1, and here you have I plus 2. So when I have I plus 2 is equal to the last value n minus 1, from here we can say that I is equal, so you take 2 to the other side, and you will have n minus 3. So the value for here will be n minus 3. So substitute this one in here. Then, since this summation starts from 1, then we can say that the summation of I equal 1 up to n minus 3 of I plus 2, we distribute, and this will be equal to summation I equal 1 up to n minus 3i plus summation I goes 1 up to n minus 3 of 2. So this is equal to, for this summation, the new one, just remove in this equation, see? Now in this equation, remove n and replace it by n minus 3. So this will be equal to n minus 3. And when you put here n minus 3 plus 1, it will be n minus 2. So you will multiply it by n minus 2 divided by 2. Now for the second term, here this is a constant. So you can take it outside. So the question, how many numbers do we have from 1 up to n minus 3? By subtracting both of them, n minus 3 minus 1, and then we add 1, the answer will be equal to n minus 3. So that means we are going to multiply 2 by n minus 3. Do the simplification and you will have a closed form equation for this summation. Similarly, for the geometric sequence, let's consider the following example too. So, as an example, find the following two summations. So find the first summation, I goes from 0 up to n for 3 raised to power I, and the second one, summation, summation does not start from 0, but it starts from 1 up to n, 3 of I. So here we can put any number, but I will put just n and see how we can find the closed form equation for these two geometric sequences. By writing the geometric sequence from 0, remember this is the one we have Ri. Now R is equal to 3, so it is summation 0 up to n minus 1, 3 raised to power I, which is equal to 3 raised to power n minus 1 over 3 minus 1, which is 2. Maybe I should write it explicitly from the rule. So here we have 3 minus 1. This is from here, the geometric sequence, which is this one. See, I starts from 0, it goes up to n minus 1. So don't look for n minus 1, just look for the start. So what we will have here, okay, for the first summation I equal to 0 up to n, 3i. Now since it starts from 0, see the relationship between this number and this number. I will write it in a color so that it will be clear to you. Now see how we are jumping from here to here. We are in fact adding 1. Do the same for any other one. So if you write, for example, if you want to find from n, then you add 1. So your answer will be equal to 3 raised to power n plus 1 minus 1 over 3 minus 1. So just simply put whatever the value here plus 1 over n. And this is the only n we have on the right-hand side equation. Now for the other one, make the adjustment so that it starts from 0, because our original geometric sequence starts from 0. I will surround our original geometric sequence. So to link the answers for the new ones. And now this one, the new one, starts from 0. I need to make the adjustment, because if I is equal to 1 on the left-hand side, the first value for 3 will be 3 raised to power 1. So if I put just only 3 raised to power I, then the first value will be 1, not 0. So how to make it start from 1? So we add 1. So here now if I is 0, then we will have 3 raised to power 1, which both will start from the same number. Now for the last number in the sequence, like what we have done for the arithmetic sequence, plus 1 is equal to n. Why n? because see, this is the one we want to find. It goes up to n. If I want to make I plus 3 reaches n, then solve this equation. So I is equal to n minus 1. Now substitute. So we have summation that I goes from 0 up to n minus 1, 3 raised to power I plus 1. And this is equal to, now this is a 3, this one is a 3 multiplied with 3 raised to power I. And you can take a 3 outside the summation. And this will be equal to 3 times summation I goes from 0 up to n minus 1 for 3I. Now here apply the geometric sequence here. So if you want to see, starts from 0. So all what you have to do, just add n minus 1. And you will have on the right hand side a 3 multiplied by 3 raised to power n minus 1 over 3 minus 1, and this will give us the answer. The other rules of summation that we need to review is first is if we have a constant k multiplied by a function in terms of I, and not necessarily that this is a constant, maybe an equation, but it has a variable not equal to I, then you can take it outside. Now if you have two equations in terms of I, so you can distribute the summation over them. So if you have a plus and minus, you can distribute the summation. But if you have a multiplication of two functions, then you cannot distribute the two summations over these two functions. For the closed form of summation that goes to I, it's equal to n multiplied by n plus 1 over 2. Now the closed form equation for I squared, because we will use this equation for some examples later, it's equal to n multiplied by n plus 1 times 2n plus 1 over 6. Now if you want to remember this equation, then n multiplied by n plus 1, this is coming from summation of I. And 2n plus 1 is an odd number. See how odd numbers are represented? 2n plus 1 divided by 6. Now for I cube, it is simply what is inside is the summation for I goes up to 1 up to n. And this, if you remember, it's n plus 1 over 2. So for a cube, it is the summation that goes up to I raised to power 2. By this time, we have finished today's lesson. In the next lecture or lesson, we will show you how to find solutions to recurrence relations.